So a rancher wants to enlarge an existing rectangular corral such that the total area of the new corral is 1.5 times that of the original corral. The current corral's dimensions are 250 feet by 160 feet. The rancher wants to increase each dimension by the same amount. Okay? So, what did y'all kind of come up with? Hold on, let me, oh, there it is. Yes.
For the equation?
Yes.
I got A of x equals 250x times 160x.
Okay, so A of x is equal to
250 times
250
x.
x.
Yes. Times 160x.
Times 160x. Okay. Now let's see. Let's kind of break this down. I think that's definitely on the right track, but let's see. So if the total area of the new corral is 1.5 times that of the original corral, okay, so it's kind of like you have the original area times 1.5 is going to give you your new area. Just kind of write now kind of what I think there. And the current corral's dimensions are 250 by 160. So, and they're increasing each dimension. So isn't it going to be each dimension by the same amount, I should say. Let's call that amount what? What can we call that amount? X. Okay. So what can I do to the 250?
I multiplied 250 by 160 and by 1.
Or could you do A of x equals 60,000 and then just do 250x times 160x equals 60,000?
So you want to set this equal to 160,000 right here?
Or just 60,000. That's what I got.
Oh,
I did
60,000.
40,000, which is their
Okay, gotcha.
current area.
Okay,
times
very good.
1.5.
Okay, now, so you're saying that the area after the increase is going to be what? 60,000. Okay, very good. Very good. Now, here's the thing though. Do we want 250 times x right here or plus x? Okay, let me draw it out for you. Let me draw it out. So I have my original corral and it's going to be, let's say 250 and then 160. Now I'm going to increase it this way and this way, correct? By the same amount. Y'all with me? So then it's going to give me, now I don't know if I drew that to scale, but my new area should be 1.5 times the original area. And the original area would have been what? 40,000. So this area is 40,000. So 1.5 times that would be 60,000. So I think that what I want is to add x both of those for both of those dimensions, correct? So I get that, and then this. Okay, so really what I have is x plus 250 times x plus 160, and that should equal 60,000. Okay, now what would I do with this? Okay, now, okay, if we have the graphing calculator, do we really need to multiply it out? No. No, we can just put it in the graphing calculator and just subtract the 60,000 over. So what I'm going to do is in my graphing calculator, I'm going to basically do 250 plus x times 160 plus x, right? And then subtract the 60,000. Okay, so you were definitely on the right track. It's just instead of multiplying for area, you think multiply for area. But it's the fact that the original dimensions had to increase, so you would add the unknown x to both dimensions, both of the two dimensions. Now, let's get our graphing calculator. I have no idea what's going to work here. So you just kind of have to play around with it and graph it. So I did.
I got a U if you want. Change it to like 1,000 for the X min and max.
Okay, so let's go with negative 1,000, positive 1,000. And then what about for the y's?
And that is 100,000.
100,000. Because the area is what our function is determining or estimating. So it's going to be a bigger amount. Very good. So our y's have to be bigger. And then graph that. Did you do 100,000? Okay. So there we go. Now, is that the way everybody's looks? So we've got to solve for this for what? What are we trying to find? The x that will accomplish increasing the area by 1.5 times. So I need to find this x right here, correct? Okay.
Could we do a value of 1.5? Or are we not trying to find one?
Well, and remember what this is right here. This is 1,000. So this may not be as tiny as what it looks like. Now, we took care of the 1.5 in the setup of the function because we set the function equal to 60,000. So we had already multiplied by the 1.5. So all we want is that location right there. So just do second, calculate, and we're going to find our point of intersection. And I'm going to do 0 for the left bound. And then maybe I'll do like, I don't know, 100 for the right bound. And I just need to make sure, and that'll work because it's to the right of the x-intercept. So I'm basically saying left bound here, right bound here, and then it says to guess, or did I already guess? I think I did it too fast. So I'll do it again. Second, calculate, intersect, and I'm going to do 0, 100, or what in the world? Sorry. So second, calc, intersect, I need 0. Why does it keep doing that? Okay, so we'll do it a different way. Let's just find our 0 instead of trying to find the point of intersection. So go to the left, press enter, go to the right, press enter, and then press enter again. So it's 44.05. And that will solve that function, 44.05. Now, so let's go back and kind of talk about what we have here. So 44.05. Now, if we want to round, we could just do 44. Are y'all okay with that? So what would our new dimensions be? 204, and it's going to be in feet, right? So 204 feet by what? 94 feet. Now, if you multiply those two out, what do you get? You should get roughly 60,000 because of the rounding issue, but it should give you roughly 60,000. So somebody do that for us real quick, make sure that works. Okay, yes, really close. Now, when we go back to the graphing calculator, because this is sort of like blending word problems with inequalities, when I look at the graphing calculator, I want you to think, what is happening with all of these x's? Anything larger than 44, what's happening? Very good. The area is more than what was requested. It's something higher. So it's giving us positive values, which means our y is positive. Okay, because what we did was when we subtracted the 60,000 over, when we subtracted this over to the other side, basically it set it equal to 0. So anything larger than 0 for the y value is saying it's a volume more than an area more than 60,000. Let me show you one other thing. I want everybody doing this with me on the calculator. I'm going to go back to my function, and I'm going to take away the subtract 60,000. So just delete all of this. So delete. Now what I'm going to do is I'm going to put a line at 60,000. All that just happened, guys, is my graph just went up 60,000. See what happened? You can kind of see it there. Now, when I graph both of these at the same time, I'm pretty sure my y should show this, the way I have it set up. And there you go. Now, where is my solution here. It's this point of intersection. So before I was thinking ahead to what I was going to do at the point of intersection, but I really should have just been finding the zeros. But basically when you subtract 60,000, this quadratic just shifts down 60,000. And what happens is this point, this intersection point becomes your x-intercept. Okay? So conceptually try to make sure you can get your minds around that. But let's do second calculate. Now I'm trying to do the intersection. And you basically for this one just kind of go close to it and do enter, enter, enter like that and see it's the same value. But now you can see this is the 250 plus x and the 160 plus x multiplied together. So this is my area function. And any x to the right of 44 is going to give me area that's what? Greater than 60,000. And then what's going on between here and here? Will all of those work? They will give me areas, but they'll be less than 60,000. But what's going on down here? When it dips down below, is that okay to have a negative area? No. So this is modeling area, so I can't have any negative values. So where it equals the 60,000, the line at y is equal to 60,000 is where I'm going to design my x at that. Now, could I use this one over here? It's a negative x, so it won't work in the domain because the domain of this has to be positive, okay? So truly, any x from here to here is going to work and give me a positive area, but only the 44 and higher would give me a area at least 40,000, okay? So that's kind of what we're doing today with the word problems, okay, that we're going to be doing. So let's go back. Monday's homework was from the workbook, okay? It was not as important, so I don't want y'all to stress about that one too much. So let me show you. So right here, here's the key, and y'all should have checked it online. Now, for word problems, we're really not going to usually make you do synthetic division and everything. You're usually just going to use your graphing calculator. Okay, this is just learning and providing opportunities for y'all to think. So here's page 120, and I would not worry too terribly much about number 4. It's kind of a weird problem just to get you to think outside the box. So are there questions on setting up the function for volume and then finding a specific volume and subtracting it over? And then if you had the graphing calculator, number 3 and 4 wouldn't even be relevant. You just use your graphing calculator. So are y'all good on that assignment?
Are we going to have a graphing calculator?
It'll be part with and part without. Yes.
So for the word problems, can you get the wrong equation but get this like an answer that works but it's not the same? Because like when I did this one, it equaled 60,000, but the dimensions were different.
It could have been how you set it up. So if you did 250 times x instead of plus x, what would happen is you were talking about an increase not by a certain like footage, like it wasn't a certain, you added 10 feet to both dimensions or 44 feet to both dimensions. You were increasing them by the same multiplication factor. So yes, you could get an answer. Now your answer would not be right because we were adding to the dimensions, not increasing them by the same multiplication factor. Okay, so let's, if y'all are good with that, I am going to give you credit for doing that, but I'll do that in just a minute. And then this is yesterday's, and I hope y'all were able to look at the key and kind of make sense of it. And this really was from the warm-up we did on Monday. So if you were out Monday, then that might have been a little challenging for you. Now there's a lot here, and this is very relevant to the test. So you do need to make sure you understand all these.
I did some without calculator and some with calculator. I don't know.
Let me double check what you will be able to do. This is definitely the no calculator page.
What the last part?
Wait a second. No, wait a second. Hold on. Some of this is on the no calculator, and then word problems that pertain to this are on the calculator part. Yes, Trey Lamb, sorry.
Is it fun if we show like where they're positive and negative through like inequality expressions, like sub value is less than x, which is less than
So you're talking about instead of, for example, B. B could also be written as what? Like, how could you write that?
it could be, for instance, -2 is less than x, which is less
Yes. So this would be x is in the middle between -2 and a -1. And you would not show inclusion, so you wouldn't underline this. So parentheses go with the less than or greater than sign without the equality part of it.
Do we have to put the
I am trying to remember if we make you, I don't think we tell you either way. Interval notation, though, is important, and you will see it on like standardized tests. So as long as you understand both, which way is not important as long as you could do both, okay? Unless it specifically says to do it a certain way.
so you won't count off?
Unless it says it, okay? Okay, so any questions on this and on doing the sign charts? There's some tricky ones with the sign charts, so there's a lot of writing up there, but yes. Okay, number 7. So if I'm looking at number 7, I'll just kind of do it from almost like from scratch here. It- Can you, on the graphing calculator? Okay, you can technically, yes. Y'all understand the question? The question is, for ones like number 7, could you just sketch a graph and see where it's above or below? Were you here Monday? Okay, y'all remember I did it both ways on Monday? I showed you first with the graph, but then I also showed you the sign chart. Just make sure you know how to use a sign chart because you're going to have to use it next year, and Mr. Campbell or Miss Willoughby don't want to have to reteach you, okay? So the sign chart would be such that if I wanted to plug in, now this is a kind of different story because really we really have something being squared here. So you can either do it with a square there or you can do 2 like that, okay? If I plugged in a -2, do y'all agree the interval from -infinity to -1, -2 would work in that interval? So if I plug in a -2, I get a negative here, -2, I'd get a negative here, and I would get what? A negative here. So in other words, x minus 3 would give me a negative times a negative. But this will always do what? Change to a positive because of the square. So I end up with this being a negative underneath because negative times negative times negative. 3 or 5 or 7 negatives will always be negative. So there's that one. So the first thing you're going to do is you want to put your x-intercepts on the number line if you're doing a sign chart. Then you pick a value in each interval and test it to see whether you get a positive or negative. Also, you know this one opens up, and you guys already know what the behavior does. What's happening, let me erase this. Let me just do this from on a blank page. So I have x plus 1, and then I had what, x minus 3 squared? And I was looking for what, greater than or less than? I can't remember. Greater than 0. So if I were graphing this, I have something at -1, I have something at positive 3. The degree is 3, right? And the end behavior should be just with a positive lead, so it's going to go down and it's going to go up like that. And then this is a simple multiplicity, so it travels and then it bounces here. Okay? Now, where is it greater than 0? It is greater than 0 here, like this. And then it's greater than 0 here above. So I've kind of identified on the graph where it's greater than 0. So it's going to be -1 up to the 3, not inclusive though, because what happens at a -1? Well, it's no longer greater than 0, it's equal to 0. So I don't want to include that in union with 3 to infinity like this. So that's how you would do that. And if you're using the sign charts, and I'm not going to actually, I may tell you to set up a sign chart, but if you could sketch a graph and just say negative, positive, positive, that's just as good, okay? Just make sure you know how to do the sign chart. Yes?
So when it's square, it will always be positive.
Yes. No matter what you put in, it'll always turn positive. And see how that plays out in the graph? Isn't that neat? That always plays out that way. Okay, so there's that one. And then check these down here. Now, some are given to you factored because they may not be factorable. There may be something that you would not know how to factor. Others are given to you where you have to factor them. So make sure you know you're factoring, of course.
Miss Morgan,
Uh-huh.
can you scroll off just a little bit to number 4? I was a little bit confused about number 4 because there's an x squared plus 6, but there wasn't for A, there wasn't anything done.
Okay, I am so glad that Brock asked that question. It is imaginary. So you just basically ignore. Now, you don't ignore this for the end behavior. Like when you determine the end behavior, you're looking at the degree of the overall polynomial. Okay? But if it's a 2 and you subtract 2, it's still going to be an even number. If it was odd, you subtract 2, it's still going to be an odd number. So it doesn't really impact things, but it is part of the degree of the overall polynomial. But you are getting what? Negative square root. You're getting what? 6 under the negative 6 under the radical, I should say. So it's going to be a positive and negative 6i. I'm sorry, square root of 6i, which is imaginary. So you would not put it on your sign chart because it's not a real x-intercept. It's not a real solution. Okay, so it has no bearing from that point on the problem. So I'm very glad you asked that question because that's important. Yes?
So because of that, we wouldn't include it in our zeros as well?
Okay, so the question is where it equals 0. It only equals 0 at negative 3/5 and at positive 1 because it physically is not on the graph. So yeah, you would include it there. This is all graphical. This is like where's the graph equal to 0? It very good, yeah.
And then also, if you have the same value or like if you have addition twice, does that always mean that the number that separates the two, does that always mean that that's going to be a tangent point?
Yeah, very good. So if you have something like this, or something like this right here, what's happening is it's bouncing there. This one would be going up like that to bounce, okay? So it's all stuff you know from the last part of the unit. It's just kind of looking at it from a slightly different perspective. Okay, now we do have a worksheet for today, but like I said, it's pretty short. And you'll probably finish this in class. I mean, that's my goal. Work with your neighbor. I'll set out the answer. I'll have it on Blackboard as well. Okay. While y'all are getting while you're getting started on this, what I'm going to do is walk around and check the other 2 days of homework. So I want to give you credit. You did the work. You need credit for it. Now, how is the review coming? Good. Because I gave it to you like what, Friday, right? So if you have not been one of those that just got started right away, then you need to make sure you work on it tonight as well.
When is it due?
It will be due on Friday. Okay, so for tonight, make sure like you'll finish this worksheet in class today pretty much. Tonight I would do as much of the review as possible so that you can hopefully have questions ready for tomorrow.
Can I get my workbook out of my locker?
Yes, sure.